Okay, so today I want to talk about improper integrals. An improper integral is just in the same form as a normal bounded integral from a to b of f of x dx, but we have two types. The first type is when a or b is equal to infinity, and the second type is where the region bounded here has a discontinuity somewhere in here. So let's go through kind of an example to get our heads wrapped around this, and then we can go through what this actually looks like. So we're asked to sketch this infinite region R. We've already done that. That lies under this curve y equals 1 over x squared. That's that line there. Then we shade it. So I shaded it and to the right some t. So I shaded between 1 and t. So we're asked to solve this integral. From 1 to t of 1 over x squared is going to look like 1 to t of x to the negative 2 dx. We solve that, we get negative 1 over t plus 1. What does this tell us about the value of a to the t? Well, it's actually close to 1, so there must be a limit here, right? So if we actually find the limit as t goes to infinity of negative 1 over t plus 1, well, negative 1 over t is going to cancel out and become 0. So this is going to equal 1. So this actually converges. And this is how we're going to solve improper integrals. We're going to use limits. So our first case is, our first type of improper integral, the one where a or b is equal to infinity, can converge if the limit exists, otherwise it diverges. If you have an improper integral where there's like two parts, both have to be convergent for the whole integral to be convergent. And if it's continuous, then a to infinity of f of x is equal to the limit as b approaches infinity of a to b f of x. And you could rewrite this here and rewrite this here and break it up into two parts, okay? So let's actually do one. The integral from 1 to infinity of 1 over x dx. We can rewrite that as the limit as t approaches infinity of 1 to t of 1 over x dx. Well, we know that the integral of 1 over x is just the natural log of x. So we're going to rewrite this as the limit as t approaches infinity, the natural log of x from 1 to t. Now we're going to substitute in t for x just like we would find just like we would evaluate any integral. So we have the limit as t approaches infinity of ln of t minus ln of 1. Well, the ln of 1 just becomes 0. So the natural log of an infinity is just infinity. So we actually know that this is divergent. Now, this is not really that important today, but in the future, we'll need this theorem. So 1 goes to infinity of 1 over x to the p. It's convergent when p is greater than 0 and divergent when p is less than or equal to 0. That will come in handy when we do series. So here's a few more examples. From negative infinity to 0 of x e to the x dx. We can rewrite this as the limit as t approaches negative infinity, t to 0 x e to the x dx. We're going to use integration by parts. So if we say u is equal to x, du is equal to 1 dx, v is e to the x, dv is e to the x, then we can rewrite this. So we have the limit as t approaches negative infinity of x e to the x minus e to the x dx. This is a 0 here. We evaluate this, or we still integrate that, so then we get this. We evaluate, we get 0 minus 1 minus, well, t, this here is going to become 0, 0. This is negative 1, which is convergent. Now, what if we have negative infinity to infinity of 1 over x squared? We're going to break this up to be negative infinity to 0 and 0 to infinity. You can do that. It's easiest to use 0. So our limit as a approaches infinity, like now I kind of skipped a step here, but instead of putting negative infinity, I put a. Instead of putting infinity, I put b. But we have the arctangent of x and arctangent of x. So here we have arctangent of 0 minus a, arctangent of b minus a. We get pi over 2 plus pi over 2, right? Because it's going negative infinity and infinity, which is just equal to pi, which is convergent. Very interesting. So we've been asked to sketch this function from 0 to 5. Why would this be improper? Well, this would be improper because at x equals 2, there's this infinite discontinuity, right? We can never have x equal to 2, but 2 is within our boundaries of our integral. So if we want to solve this integral, we're going to substitute in t for 2. We're going to use u substitution, and we're going to end up getting, after our computation, 2 radical 3 minus 2 radical t minus 2. Now we can actually find that limit as t approaches 2. Well, if we're approaching 2, we know it's from the right in this particular graph, right? So we can just substitute in. You can use your calculator if you want, but you're going to end up getting 2 radical 3, which is convergent. All right? Now, the last type that we have is what we just talked about here. When we have part of our boundary of our integral, part of our bounding includes a discontinuity, right? So we can write that a to b as c approaches b from the left of c right here. So let's just do 1 to c. From 0 to 1 of the natural log of x dx. Well, natural log cannot be 0, so I'm going to put an a for 0. So from a to 1 of natural log of x dx, I use substitution here. I get the limit as a approaches 0 from the right of x ln of x minus x. I evaluate. Then I substitute in that 0 from the right, so we get -1, which is convergent. Here we have from 0 to 3 of dx over x minus 1. Now, because this one doesn't have our boundary clearly written out, or it does have our boundary clearly written out, but our discontinuity is included within here. It's not actually just discontinuous at one of our bounds. We need to rewrite this from 0 to 1 and then from 1 to 3. So we do that, and we're going to use our limits from 0 to a and then from b to 3. Okay, so we're approaching from the left and from the right. Once we evaluate that, we then take our limits, and we end up getting this does not exist. It's divergent because this is -infinity. If this is -infinity, I don't even need to solve this because I know that both have to be convergent in order for the whole thing to be convergent. If one's divergent, the whole thing is divergent. So that's how improper integrals work. Hopefully this helped clear things up a bit, and I look forward to seeing you in class. Bye!